Good morning, everyone. I want to talk about the citric acid cycle. If you remember, we ended glycolysis by forming pyruvate, and then we had this intermediate step that I had right at the bottom, where pyruvate was changed into acetyl-CoA. As long as, what was the requirement? As long as there was oxygen, right? We couldn't do it if there wasn't oxygen. We formed lactate instead, right? But if there's oxygen, we're forming acetyl-CoA. So here, at the citric acid cycle, we're going to start with acetyl-CoA. And acetyl-CoA is going to combine with something called oxaloacetate. So oxaloacetate is 4 carbons. Acetyl-CoA is going to be 2 carbons. And we're going to combine and have a 6-carbon citric acid. Citric acid is going to go through a number of oxidation reduction reactions that I'm not going to require you to know. I believe in microbiology you'll have to know this. But for us, what I want you to know here is acetyl-CoA combines with oxaloacetate and you get citric acid. Oh, and look what it's called, citric acid cycle. You may have called it the Krebs cycle at some point, but it's easier to call it citric acid cycle since it's something you have to remember anyway. Alright, so during this cycle, we're going to produce a number of NADH. So NAD plus is going to get reduced to NADH. And it's happening along the way. But look what else we're going to produce along the way. Carbon dioxide. Every time we go around, two molecules of carbon dioxide. And here, yay, ATP, we're producing ATP. And here, remember we discussed at the very beginning in the background information lecture that FAD and FADH, FAD becomes FADH to become, or FADH2 I should say, to be an electron carrier. So not only are we making NADH, we're making FADH2. And another molecule of NADH. Alright, so my question for you is this. For one glucose molecule, how many pyruvates did we make? We made 2, didn't we? So how many times are we going to go around? Twice, right? So let me see. So we'll do the first time in orange. 1. Alright, we make an NADH, another NADH, 2 CO2s, 1 ATP, an FADH2, and another NADH. And we're coming around, and look what we make along the way. Oxaloacetate. And that can combine, let me get another color, right there with acetyl-CoA. And we go around again. Alright. So to figure out how much you make per glucose molecule, you actually have to go around twice. And over here I have totals. Alright, how many NADH? 3 each time, so a total of 6. How many FADH2? 1 each time, so a total of 2. How many ATP? 1 each time, so a total of 2 here. But look at this. We make 4 carbon dioxides. I find this really interesting because what did we start this section with? What's the first chapter on this exam? Respiratory, right? And what does the respiratory system do? It does deliver oxygen, which we needed, well, for this stuff as well, but to get to this step we needed oxygen. And carbon dioxide, it removes the waste, the carbon dioxide. So you see how metabolism is so intertwined with respiratory. So isn't that interesting? I love this section. That's why I put respiratory, digestive, and metabolism together. Because what does digestive do? That supplies the fuels that we're going to be breaking down, right? And respiratory delivers the oxygen needed to break them down and takes away the carbon dioxide afterwards. Now we'll also talk next next unit about the urinary system and how it removes other wastes. But I find this very fascinating, and I love how we can actually see where the carbon dioxide is coming off. So this is the citric acid cycle, sometimes called the Krebs cycle. You're starting with that acetyl-CoA that you made in the intermediate step after formation of pyruvate during glycolysis. It combines with oxaloacetate, makes citric acid, a 6-carbon molecule. You go through a series of reductions. You lose a couple carbons here to carbon dioxide, and you're forming each time around 3 NADH, 1 ATP, and 1 FADH2. Now I have a question. Why am I making a big deal about NADH and FADH2? What's the point? Well, remember we talked about electron carriers? That's what these are. But where are they taking them? What's the purpose? So these are going to the electron transport chain. To the electron transport chain. And once it gets there, then that's the true ATP maker. We'll talk about that in the next video. So it's significant that we're making these electron carriers because we're going to take that to the electron transport chain, and it's kind of like if you were at, I don't know if Chuck E. Cheese has little tokens, but I believe, if I remember, they do. So let's say you're at some sort of game place, and you get tokens, and then you give your tokens to the counter, and they say, oh yeah, here's your cash. So this would be similar. You get these tokens, they take it over to the electron transport chain. That's the cashier, and they say, oh, you have this many tokens, we're going to give this many ATP for it. Does that make sense? So that's the whole point. These are our tokens, taking them to the cashier. All right? This is what I want you to know for citric acid cycle. I know the picture in the book has a lot more detail, but I feel this is enough, especially since I know you'll learn a lot more about it in microbiology. Thanks, everyone. Goodbye.